Welcome back for part 2 of 6.0 Digital Locksmithing, Cryptography, and Encryption. So let's just jump right in with advanced cryptographic techniques. Now again, don't worry, we're only covering the surface. This is a career in itself. This is a doctorate degree in itself when we talk about cryptography, becoming a cryptanalyst, etc. So here we're talking about algorithms, and this is what makes, these are those mathematical rules, okay, that basically form our cryptographic methods that we use today, okay? The more complex the mathematical equation is, the more complex the cryptographic method is. Now remember, as we'll look at, we need to use different cryptographic methods depending on how much we need to encrypt a message, decrypt the message, the time it takes to do that, especially as it traverses the internet. I'm so old, I remember, and we're going to be talking about this, I remember DES encryption and how absolutely slow it was to encrypt a VPN connection so that I could work remotely when I was out of town or out of country. So, algorithms, set of well-defined instructions or rules designed to perform a specific task to solve a problem, often derived from mathematical principles. So if you pick up my book, there's a couple case studies in there, one of which is the cipher, or the cosine, specifically the discrete cosine transform, which is the algorithm that was created to compress images. So great read on that. In context of cryptography, algorithms are used to encrypt and decrypt information, ensuring data security and integrity. So again, bringing back the CIA triad, right? So in the case of the Caesar cipher that we used previously, it demonstrates how algorithms can transform readable data into an encoded format, and it really is today much more complex than the Caesar cipher we use. Now, algorithms are not just about encryption, okay? Some of you may be familiar with the Google algorithm and the Google algorithms. So, pre-2011, any content, inbound links, it just continued on adding relevant content. So we're not getting, 4 million cat hits when we search cats on the internet. Now we're getting specific cats, etc. And it just continues to grow, all the way up to 2019 with neuromachining. So amazing algorithms. And algorithms, again, can be used for other things besides cryptography. They can be used to sort data into more valuable information. Okay, so as I mentioned, the algorithm we can think of as a noun. It's a thing, right, that we use to encrypt. And again, for you cryptography experts, we are keeping it simple here for the foundation of the ISC2 exam, all right? So serve distinct purposes, process of ensuring and maintaining data privacy as we use them together. So our first real key method is the symmetric encryption, and it's an algorithm that uses the same key for both encryption and decryption. This makes it highly efficient, okay, however limited. So, efficient, widely used for securing data where both sender and receiver can safely share the key. So this might be within an internal secure network where we just want to encrypt traffic between a machine and a server locally. Okay, so again, closed networks. We can also use the asymmetric encryption algorithm for locking down data, say on our smartphones, as we'll see. So early versions of symmetric encryption, here it is, DES, Data Encryption Standard, which wasn't very secure. It worked on what was called the RC4, which we'll get into, the RC4 cipher. And shortly after being released and used in Wi-Fi security standards across many manufacturers, well, that key was broken, and WEP, Wireless Equivalency Protocol, which was used for securing Wi-Fi, was no longer technically secure. Matter of fact, it was the first thing that I learned to hack was how to get that key, and decrypt messages across that were using DES. So that brought forth, hey, here's an idea. Let's just do that 3 times, which means 3 times the overhead when encrypting, 3 times the overhead with decrypting. That VPN connection got even much more slower. But, this was original encryption. It was used by banking systems. It was used as Wi-Fi standards and for VPN connections. Today, definitely unsecure. So hopefully you don't wind up finding a Wi-Fi device router that's using WEP. If you do, get rid of it. Get rid of it quickly. But before you do, check the logs because somebody's probably in that system. So, AES is a great example here. So prominent symmetric encryption algorithm that is highly used today. Full disk encryption. You're going to see this on your smartphones. I think both Apple and Android use this technology to encrypt the data while it's at rest on your phone, while it's being used by your phone. So if somebody gets your phone, they can't just pull that data off, right? Works for secure boot. We can use it for app protection. Modern Wi-Fi security uses it. WPA, now WPA3, secure data transmissions between devices in a wireless network. So those are our new Wi-Fi standards, if you will. So that brings us to the next level, which is asymmetric encryption. And it is similar, except it uses a pair of keys, a public key and a private key. Okay? So, secure data transmission, even if the encryption key is public, as the only corresponding private key can decrypt the data. So the public key can be made public. And we'll see that, in SSL certificates. But when that data transfers to the private side, it's that private key that decrypts it. So we really have to protect the private key, right? So the public key used for encrypting data, private key used for decrypting data. And again, folks, make sure you're taking notes on this stuff. It is so great to learn when you're not just listening, when you're engaging in active writing and you're listening. Maybe you're coming back and reading the transcript of this. The more you take it in, the less you're going to have to study for that ISC2 certification, certified in cybersecurity certification. So a couple great examples. We already saw this, right? The RSA methodology, the first public key crypto systems widely used, okay? Not cryptocurrency systems, crypto systems, okay? Widely used to secure data transmission. So, transmission over the internet, you've probably heard of SSL and TLS. We're going to take a brief look at that as well. You've got a little diagram here you can look at to understand, again, public key and private key. That brings us to some different cryptographic methods. ECC, or elliptic curve cryptography. It's based off that function in math, if you will. Okay. Common uses are mobile and IoT devices. Why? It's small. It's efficient. So when we're talking about, say, Raspberry Pis or IoT devices with data we want to encrypt, RSA has a huge key. ECC has a smaller key. Okay, as does AES, by the way, which I think AES is 128-bit or 256-bit. That's why it's so efficient, okay? As we'll see as we go through, sorry. So again, I mentioned SSL, TLS certificates. You're looking for that HTTPS. You're making sure that it's there before you transfer any usernames, passwords. All of your banks better be using it. Any financial stuff, you go out and shop on Amazon, you're looking for that HTTPS, right? End-to-end encryption combines the two. It combines symmetric and asymmetric encryption methods, ensuring data is encrypted on the sender's device and only decrypted on the recipient's device. Okay, and we see a graphical representation of that here. So again, just a reminder, terms that are bold and gray followed by orange, those are terms that you may see on either in my class or on the ISC2 certification. So other examples of E2EE, so end-to-end encryption, is Signal Protocol. So we see this on WhatsApp. We see it on Facebook Messenger. You know, it's designed to prevent man-in-the-middle attacks and ensure messages are encrypted end-to-end. Pretty good privacy. Utilizes a public key for encrypting emails and a private key for decryption. So again, just some examples of where these cryptographic methods are used today. All right. Now that leads us to block ciphers, and the difference between block ciphers and the others is these limit or encrypt data into fixed blocks, which means the blocks of data are encrypted. So it's not a stream that's being encrypted. We'll look at that in just a minute. Okay, so there's a process here of taking 64 or 128-bit blocks, encrypting those, boom, they go over, highly efficient. Okay, fast, flexible. You know, variety length of keys, again, you know, typically 64, 128, but anywhere from 32 to 448. Don't know where the 448 came up. Why not 512? Well, we've got some overhead going on there. So applications, you know, securing passwords, file encryption tools, Blowfish leads to Twofish, okay? It was the successor. It was actually a finalist in the AES competition, which is kind of cool, but again, a finalist doesn't mean it got used, right? Anyway, 128-bit, 256, you know, encrypting software, cryptographic libraries use it, etc. So that does bring us to stream ciphers. And stream ciphers encrypt data as a stream. So imagine that data from Netflix being encrypted coming down to your computer, okay? You know, suitable for continuous data flow. Now, an example of this was that RC4 cipher. It was, again, continuous data flow. It was continuously encrypting Wi-Fi traffic between the router and your device. But again, unfortunately, right, WEP was hugely insecure when the RC4 cipher gets, you know, they basically figure out how to decrypt it, how to decrypt the RC4 cipher. So that brings Salsa 20. Most of the time you're going to see Cha-Cha 20, developed by Daniel Bernstein. Hey, Daniel, how's it going there, buddy? And applications that use that should look pretty familiar. Android, OpenBSD, and your browsers. Chrome, Safari, Firefox, VPNs such as NordLayer and Surfshark VPN, all are using Cha-Cha. Just a few more methods, not really, you know, that you need to know a lot about here, but attribute-based encryption. It's basically encrypted by users' unique attributes. It really provides some flexibility in encryption, okay? Format preserving encryption. This is kind of weird to explain. It basically encrypts data while retaining the format of the plain text. Yeah, let that sink in for a minute. And then, you know, again, newer technologies that are coming out, if you will. And homomorphic encryption allows computation on ciphertext, generating results that match the plain text operation. So highly efficient, if you will. Okay, so again, you might want to do a little bit more reading on this. Pause, you know, ABE, KPABE, etc. So that's it for section 2. In section 3, we will take a look at hashing, digital certificates, and secure communication channels. Until then, have a great day, and I look forward to having you listen, having you watch the next video. Take care.